Start another video. Great. So the idea is that basically it's easier not to do timestamps if I can just break this up into segments. Okay. So how in the world do we solve these? Well, this gets into something called recursive backtracking or exhaustive recursion, because we need to look at all the options and we're going to use recursion to do so. And honestly, that's why I asked at the beginning of class, do you have your laptops and are you ready to do some work on it? Because honestly, these are a pain in the butt to show you. Except Sudoku is actually pretty easy to show you. So I'm going to show you how this works, how we can solve Sudoku using something called recursive backtracking. You did this with stacks, right? And your mazes. So let me just go ahead and look for. Let me go ahead and pull up our maze generator. So maze. So sorry, Eclipse. So I'm going to show you an example of how we did this, and then I'm going to show you how the same algorithm can be generalized and then applied to Sudoku. And then you may be able to see how we can apply it to the chess problem as well. And then we're going to work on a slightly different problem that we're not going to do for homework, but it's has a very similar concept. Okay. So source. Oh yeah. So I wrote a Sudoku solver a while ago, and I can show that off at another time, just not when the code will be displayed online for you to copy. So, so let's see. Right, it was in teaching, I think. Yeah, so stack maze. So let's just run our maze program, and that was a 50 by 50 maze, which is a bit hard to show on the screen. So let's go ahead and do a 7 by 7 maze. Okay. Now the way to solve a maze, right, using this recursive backtracking process, was essentially that we would look to go to the north, then to the then we'd basically look to go up, right, down, and then left, right? Or some other order of that direction. Essentially, you ask yourself, let's see if we can go to the north. Up, no. Can we go right? No. Can we go down? No. Oh, wait, right? Yes, we can go right. So we'll go right. Then we ask ourselves, at this grid location, can we go up? No. Can we go right? Yes, we can go right. Can we go up? No. Can we go right? Yes, we can. Can we go up? No. Right? Yes. Can we go up? No. Yes. No. Yes. No. Yes, no, 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 and we've already visited that one, so we can't go that way. And the idea here is that we hit a dead end right at this point, so we can't go any further. So we would pop off the stack. And now, remember, recursion uses a stack as well. It just uses basically one built into the computer, so it just pops. So essentially, we would just return false there to say, hey, choosing this path did not solve the puzzle. What we'll do is that we'll return true to say it did solve the puzzle. So return false. We're at a dead end. Return false. Okay. Well, I'm going to call solve on this location and then go this way. So can I solve it this way? Okay. Can't go up. Can go this way. Return false. Return false. Return false. Come down. Go this way. Return false. And essentially what we're doing is we're essentially checking in a very methodical manner all possibilities, right? We're checking, can we go north, south, can we go up, down, left, and right? Can we go in those directions? And we have a specific order. And once we find out we can't go into those directions, we back up and ask, can we go into a new direction? Okay? Does it make sense for everybody? And so that's the way depth first search works. We kind of just have this algorithm that says, basically, can we choose for every single can we look at all the options and can we do those options? And I'm going to show you kind of how that looks on Sudoku now, and then I'll write a very generalized algorithm on the board. Okay, so let's go ahead and look at Sudoku. So let's say you really want to be like me and solve the Sudoku puzzle, but logic is stupid. So what we can do is we notice that this is a grid. So what we're going to do is that we're going to go line by line. So for each row, we're going to go through each column, and then we're going to solve each thing in the column, right? So this one's already given to us, right? Because in order for it to be a puzzle, for it to have a unique solution, some of the stuff has to be given to us. Counterexample is that if we were given a blank puzzle, we could just fill it in however we wanted, right? So that's kind of boring. So so this is solve, skip, solve, skip, solve, skip. Oh, okay. So now what we'll do is we'll pretend we didn't fill that out. Let's just go ahead. How many choices do I have here? Well, I can put any of the numbers 1 through 9 in. So let me just roll my finger across the keyboard. Aha! There's a 4 there. I've solved that one. So I'm going to assume this one is solved and move on. and I'll see if I can't solve it any further. So 1, 2, 3, 4, 5, 6, 7, 8. Can't. Oh, could put a 9 there. And now let's try to put 1 there. Aha! Let's go on to the next line. Okay, that's solved. 1, 2, 3, 4. Up 4. Couldn't put a 9 there. 1, 2, 3, 4, 5, 6. So you know what so I just continue on, and basically I'm saying, hey, it doesn't get interesting until I hit a dead end, right? I'm just going on line by line, and I'm just simply putting in something until I get to a dead end. 8. 4 there. This is one of these easy ones, so you know it's I can get pretty far on this, I think, just by doing random stuff. I'll be highly disappointed if we get to the end and I don't have to back up at all, because that says something about the difficulty of this puzzle, and it completely. There we go. Right, so we selected. So basically, we went through each thing, right, and we just simply selected all the options and we went with the first one that worked, right. This is what we call kind of a greedy choice, right? We just simply assumed that the first thing we would choose would work, and then we'd go with it until we hit this dead end. Can't put a 9 there. We can't put any of the numbers there. So we delete our choice over here, and we're going to back up. We're going to backtrack to our last point, right? So what happens is that basically this square calls this square, which calls this square. It says, so we're going to start by solving in the top left corner, okay? And the solution is, so how do I think of this recursively? The way the recursive thinking goes is that I'm going to solve my square, right? Consider each square to be their individual, kind of an individual player in this game. And each guy goes, I'm going to solve my square, right, recursive. And then I'm going to solve the entire puzzle recursively by calling the next guy down below. I'm going to solve the rest of the board. So he goes, okay, I've got my square solved. I'm going to call the rest, and I'm going to solve everything but this square. And he goes, I'm going to solve everything but this. Now I call recursion on everything but this square, right? I've solved this one. It's 4 here. I'm going to solve everything but, you know, the things after me. So we got to a dead end over here, and this guy said, you guys led me into a dead end. There's nothing we can do here. So he's like, uh-oh. So he returned false for his solution. That meant that basically we have to keep going. 6, 7, 8, 9, uh-oh. So I have to backtrack. Uh-oh. Okay, so it was at 7. We can go to 8. So then we can continue forward. 1, 2, 3, 4, 5, 6, 5 can go there. 1, 2, 3, 4, 5, 6, 7. Aha. 1, 2, 3, 4, 5, 6, 7, 8, 9. Aha. So we got a bit further just by backtracking a bit. 9. We got a 1 there. Right? And so I'm just simply moving forward. I'm going line by line and just simply going through all the options for each square until I find something that works. And lo and behold, I eventually find something that doesn't work. So I have to increment over here. That doesn't work. And so this takes me a while to do. But for your computer, it's going to be able to solve it like that, right? It's going to be able to solve it very quickly. So what is this algorithm? It's called recursive backtracking. And it's the same thing. It's actually the same algorithm we use to solve a maze. It's the same algorithm you're going to use to solve the chess problems. And it looks something like this that I have on the, I have it written down here, classroom. And I put it in terms of boards because that's the way we work with most of the board. We work with mainly boards here for our examples. Destruct, don't know why I closed the file, but assignments, recursion. Here we go. So our algorithm looks something like this, which again, because this is being displayed on the screen, they'll be able to capture it. Basically, so this is our backtracking algorithm. It says Boolean solve some board position. Board being like something like our cells or our chessboard or the Sudoku grid, right? Okay, basically it's basically the thing that we display our solution on, okay? And position is where we currently are, okay? So, and remember what this is. So let's consider, like, for these puzzles what the base case is. Like, when can we say we're done? Base case for the maze is if if I'm here, I'm done. If I'm in the bottom right corner, if I hit a red square, I'm done, right? That was our base case there. In this case, and here that would be like I finished all the boards and now I'm not over here, right? I'm out of bounds. Then I'm done. In chess, it's the same way. If I've got for the chessboard, it's like I'm out of the board. So if position is true, if position is such that there's nothing left to solve, in other words, I got to the end, return true. Tell everybody else I'm done, right? We solved the puzzle. Good job, guys, right? Otherwise, we haven't solved it, right? So I have to figure out what my solution is. In Sudoku, there's one other base case, which is if my square is already filled, skip it, right? So for each possible choice, for each possible choice, so for here, it's in our maze function, it's going north, south, east, or west, right? That's a possible choice. Let's see, for our Sudoku puzzle, that's putting a 1 through 9 on the square. For the chess problem, it's where we're going to put a queen in this column, right? Because what you want to do is go column by column, essentially. So which row are we putting a queen on essentially? I'll get into that in a bit more detail. And for the knight store, it's each possible choice is where I can move, right? So for each of those possible choices, essentially, so for each possible choice, so we'll go through them in some order, right? So for mazes with direction, if that is a valid choice, and what's valid depends on the context. For that means, can I put a queen down safely in the chess problem? For the knight's tour, does that mean have I been there before, or is it even in bounds, right? Is it even is it even on the board? For the Sudoku puzzle, that means is it a number that's already taken, right? I can't put an 8 here. That's not a valid choice. But if the choice is valid, then I mark the board at that position with my choice. In other words, here in this case, basically, if I have a valid choice over here, what I did over here is that basically I looked at each choice. This wasn't valid, so I kept going. This wasn't valid, so I keep going. This wasn't valid. This wasn't valid. This wasn't valid. This wasn't valid. That's valid. So I mark the board at that position with my choice. And then I do this is the hard part about this, I feel, which is if solve board position plus 1. Essentially, I call over here, I recursively call this, we're solving the same board, right? So no need to change that. But now my position is the next position, whatever that might be. We might have to wrap around, right, if it's rows and columns. But if that returns true, that means if I get a true back from the rest of the people solving the puzzle, that means we're done. Whatever I chose helped us solve the puzzle and we're done. Okay? Otherwise, well, that wasn't a valid choice, so I've got to continue. So next I got to check the next choice. Right? If it returns false, I don't do anything. Instead, I continue doing the loop. I check the next valid choice. Is that valid? Oh, if so, I'll call the next one. What if I go through all my possible choices, though, and I don't have anything that works? Right? What if I get to a dead end? Well, in that case, I clear any choices I marked down. So here in this case, it would be like getting to here, right? So I put down a 3 there, and then I put down a 4 there. Right, I get all the way here, nothing worked. So at this position, I want to clear my choice, and then I want to return false, which says backtrack on, which tells, remember, because if you do this function call and you return false, what happens? We hear the person who called me hears back a false. They don't get back a true, which means they know that the choice they made didn't solve the puzzle, so they have to try something else. Right? That's just like with the maze, where basically if we back up, right, to a certain location, if we go this way and then we back up, and we know we have to back up over here, and this guy knows he has to try to make a different choice, right? So that's that algorithm for that's going to solve basically all the homework problems. They just have to be implemented slightly differently. Okay. Okay, so that's one, and this is like one of the cooler and more difficult kind of recursive problems, or things to solve recursion. The other kind of thing that difficult problems that recursion is solved for is permutation problems or selection problems, basically exhaustive search problems, where we're looking for all possible combinations, and that's what we're going to do in class today. So